Okay, we'll start. Good morning. Okay, so today we'll talk about autoencoders and variational autoencoders. So just to remind you, we are in this track about generative models. So this is the second lecture on generative models. What we'll see today is quite important because it will be used for the last lecture to derive diffusion models. So it's important that you understand these materials if you want to understand the final lecture. Okay, so today the goal will be slightly different from the task that we've considered before. Today the goal will be to try to learn a model of the input data itself. Okay, so we'll no longer be working in the classical supervised learning paradigm where we have inputs and outputs. We just have inputs, and we want to learn a distribution of these inputs, okay, or a model of the distribution of these inputs. So we'll go step by step to go there. I will first talk about autoencoders, then about variational inference, which we have seen already last time when we talked about Bayesian deep learning, but I will start from scratch again, and then combining these two ingredients together, we'll derive variational autoencoders, which will be a family of models that we can use to learn distributions of data. Okay, so I will start today by two quotes from important researchers from the field. The first one is by Jeffrey Hinton from 2014, so it's not a recent quote, it's already more than 10 years old. And he's basically trying to argue about why the field should move from working on classical supervised learning problems where you have usually a large dimensional input, like an image, like a video or something. But what we want to extract out from this image is usually a very small signal, relatively small signal, it's just a class label, for example, or a scalar value if you want to, if we talk about regression. And this is if the goal of the field was to really try to build machines that are able, for example, of common sense, of really machines that are starting to understand the world, this would not be the recipe that we should follow, because simply if we were trying to build these machines from a supervised learning paradigm, we would need a lot of input-output pairs, and there is simply not sufficiently many. And so he's trying then to argue for unsupervised learning, and he says that when it comes to us human, the brain has about 10 to the 14 synapses, so connections, but at the same time we only live for 10 to the 9 seconds. Which means that we have more synapses than seconds that we live, at least on average. Okay? So that means, in a sense, we have more parameters than we have data. But how come we are still able to learn and to learn very detailed representation and understanding of the world? And so he argues that this motivates the idea that we must do a lot of unsupervised learning, since the perceptual input is the only place that from which we could get 10 to the 5 dimensions of constraints per second. Okay? So this is the first argument why unsupervised learning is certainly an important topic. The second quote is by Ian Lequin from 2016. It's in the field, it's what we call the cake slide. But it's basically saying the same thing. We need, if we want to have machines or neural networks that are able of common sense, then we need to train these machines on problems that cannot be reinforcement learning, that cannot be task framed as reinforcement learning problems, because in reinforcement learning problems, usually you have an agent that acts in some environment and perceive a lot of things, but the actual learning signal is often very tiny, very small. You may get only one bit of information after a long sequence of actions. For example, if you play a game like the game of chess, you may have to play 100 moves until you know that, okay, you have won or lost the game. And that's just one bit of signal from which you have to learn. Okay. Supervised learning has the same problem, although we get more bits of information per sample, but still we are limited by the amount of data that we can learn from, because usually these labels, they are produced by humans annotators. And so we may have data sets that have been annotated by humans, and we may have medium-sized data sets in the order of millions, but this is still too small if you want to have machines with common sense or neural networks that would learn so much more about the world or about some environment. And on the other hand, he says that if we consider unsupervised learning, then the machines can use the input to basically build training tasks where the goal would be to repredict parts of this input. And so basically, as soon as you see some input data, you can use part of this input data to learn something about the data itself. Okay? And in that sense, then we get directly as much information, opportunities to learn from as we have data itself. Okay? And we don't need labels. We are just creating the labels directly from the data. All right, so a bit more formally, what we call deep unsupervised learning is usually framed as simply it's trying to learn a model of the data, and this model can be explicit or implicit, but what is really important is that it does not require any labels. Okay? And so we may have, on the one hand, generative models that will try simply to recreate the data distribution, the raw data distribution. For example, your goal may be to create a model of natural images. And so directly, what you would be trying to do is to reproduce, to regenerate images that do look like natural images. And so in this case, you would have an explicit, you would have an explicit generative model. And the other strategy, which we also frame under the umbrella of deep unsupervised learning, is what we call self-supervised learning. So it's supervised, but it's still an unsupervised approach. And we say it's self-supervised because in this case, we would be basically defining some kind of puzzle task that require semantic understanding in order for the model to solve them correctly. And so one example of that is what we did when we consider the transformer for sequence generation. You just start from raw sentences and use these sentences as to produce supervised learning problems in which what we did was to consider a prefix of tokens, and the goal was to predict the next token. Okay, but we are creating this task directly from the input data. Okay. There are variations also in the large language model literature where previously the goal was not to predict the next, but we were masking out some word in the middle of the sentence, and then we were using all the other tokens around to try to predict the word that was masked. Okay? And you can also extend this kind of idea to images and other modalities of data. What I will talk about today and next week is mainly about the first family, generative models. Okay? So generative model, if you want to try to define them a bit more formally, a generative model is nothing else than a probabilistic model that I will denote as P, to denote that it is a distribution, and P theta, because it's a parametric distribution, it will depend on parameters that we'll have to adjust depending on the training objective. Okay? And once we have this probabilistic model, our goal will be to try to use it as a simulator or some kind of simulator of the data. Okay? So formally, a generative model is just a probability distribution over the data. So P, it's a distribution over the elements X which correspond to our data. And the theta will correspond to the parameters of the model, in our case of the neural network that we'll use to instantiate this distribution, and that will try to adjust to match the unknown data distribution. It's unknown because if we knew it, then we would not be trying to reproduce it. But as usual, at least what we have are realizations out of this distribution. We have a training set from which we can learn and trying to approximate this unknown data distribution. Okay, so this will be the goal for today. We'll try to instantiate this probability distribution, this probabilistic model, and we'll do that first today with variational autoencoders. And it's actually the same problem as what we considered last time when we tried to model a conditional probability distribution Py, P of the output given input X, Py given X. We did that with a normalizing flow, with mixture density networks also. It's the same story today, except that there will we don't have this conditioning anymore. We are just trying to produce a distribution of data. Okay? So there are many kinds of deep neural networks that you can use to generate data. So today we'll talk about variational autoencoders that have been introduced already 12 years ago by Kingma and Welling. And so at the time it was really a breakthrough. Then a lot of improvements went on, and until we reach the diffusion model family, which actually was proposed not in 2023 but in 2015 or so. But it took a few years for this work to be noticed and to reach state-of-the-art results. But today, everything that you see about, for example, image generation, like Midjourney and other tools, they are all driven by diffusion models. So this is what we'll see also next week. But of course, there is more than VAEs and diffusion models. There are plenty of other families of generative models. We've already mentioned last time, normalizing flows, and they work quite well, I would say, for low to medium size data. But if you want to use them for high dimensional data like images, they wouldn't work very well. There are other families like generative adversarial networks, which have been very, very popular from 2014 to 2020, I would say. And they really moved the field forward. But these days, they are no longer producing the best results. This course actually used to have a lecture on GANs, on generative adversarial networks, but I'm no longer covering this part. If you're interested, it's on the GitHub, and you can have a look. There is also energy-based models, which frame the problem as an energy minimization problem. I will not be covering that. And finally, you also have autoregressive models as other instances of generative models. And actually, we have already seen one instance of autoregressive models. If you look at the transformer for sequence generation, it's an autoregressive model where you frame simply the transformer as a model which, given a prefix, gives you the next word, and which you can apply autoregressively within a loop to produce and generate sequences. Okay? So the goal today will be to arrive to VAEs, and next week we'll talk about diffusion models, and the path I will take to introduce diffusion model will be to derive them directly from VAEs. And we'll see that the two of them are closely connected, and I will also try to make the connections with normalizing flows, and you can actually show that normalizing flows, or rather diffusion models, are a special kind of normalizing flows or vice versa. Okay? So that's the landscape of generative models, but one thing I've not really motivated yet is, so why do we care about generative models? Of course, if your goal is just to generate pretty pictures, okay, fine, but that may not be very interesting and important in itself. There are fundamental tasks that you can achieve with generative models. Ok. Super. Okay, it's back. All right. So what are the tasks that you can achieve with generative models? Well, the first task, of course, is to generate. Okay, so with the generative models, you can generate data, and in itself, this is already interesting because you can use this data as, for example, additional data from which you could learn other models, or from which you could explore the data distribution. Okay, or you may have simply direct applications where it's interesting to generate data for one reason or the other. The second motivation of studying generative models is that you can also use them, at least some of them, to evaluate densities. Okay, so you can use a generative model to assess if some piece of data is likely or not likely under the model that you consider. Okay, not all generative models that we'll see are actually able to or give you an access, a direct access to the density values. Most of them actually just give you access to a sampler from which that you can use to generate data, but very few of them will give you access to the exact or proper evaluation of the density itself. And of course, if you have also access to density values, you can do inference, so you can start framing inference problem, for example, to derive posteriors about some quantities of interest. And finally, or not finally, but a third application is also to use a generative model to encode priors. For example, in scientific context, you may have, you may want to encode priors that are not directly expressible from first principle, but for which you may have data and you want to encapsulate this data into a distribution that you would use as a prior. So, for example, this is the case of a problem in astronomy where you may want to express a prior over galaxies or images of galaxies. This is something that you can do easily by just looking at the skies, collecting data of galaxies, and then learning a generative model or distribution of these images. And once you have this prior over galaxy images, then you can use them. You can use this prior to do inference, for example, to do inverse problem, like what you see there in the case of gravitational lensing, where you get this kind of image and you want to inverse this image, you want to unfold this image to recover the galaxy image that you see on the left. But you can do so only if you have a prior beforehand. Okay? Questions so far about what you want to do and what you can do with generative models? Okay. Okay, so I will introduce now autoencoders, and I will do that for the purpose of then deriving variational autoencoders. And this is just a tip for you. At the exam, if you get the questions about VAEs, I do not care about autoencoders. If the question is about VAEs, you can just go straight and tell me about VAEs without following exactly the structures that I have in the slides. Okay? So autoencoders. So autoencoders is a family of models that you can use basically to compress data, and the goal will not yet be to regenerate data. Okay, so let's assume we have a data set like this of points on the 2D plane, the ones that you see in red. Okay? And so they live in some original space, which will be the space of the data, which I will denote simply as X, as usual. Okay? Now, if you see this data, it's obvious that the data itself lies on a manifold of lower dimension than the original data space. Okay? It seems obvious from these pictures that actually the data could be re-expressed as position, for example, on this spiral. Okay? And in this case, you would need actually only one number instead of two to represent more or less correctly the data that you see in red. Okay, so there is an opportunity to compress the data and to be able to do that without losing much about the data itself. Okay, so that will be the goal of the autoencoder. It will be to try to learn a mapping that goes from the original space, the original data space, to what we call a latent space, a lower dimensional space, where we'll try to maintain the information content of the data, the original data, but using fewer dimensions. Yes? PCA is an instance of an autoencoder, yes. But I will actually talk about it just in a few slides. But so the first part of the autoencoder will be the encoder, which will correspond to some function f that goes from the original space, x, to the latent space. So in the slide it's f, but usually I will use the letter z to denote the latent space or the latent vectors. And you see there in this diagram that we would be mapping these 2D coordinates onto a line. Okay. And the goal of the autoencoder will be not only to compress data, but also to learn the inverse mapping, a G function, which we call the decoder, which will take now as input latent values, latent vectors, and we'll try to, from these latent values, to reproduce data, to decode this latent into data back to the original space. Okay? And you see that for this problem, the 2D point on the spiral, this is something that we can do fairly well, that we can more or less do fairly well, except that it will not be a perfect compression scheme. It will be a bit lossy. So in this case, you see that the red points, they follow the spiral, but it seems there is also deviations that could be random deviations from the spiral. But if we map these points onto one coordinate in latent space, like this, and then we try to decode them, then part of this information will be lost. And so what will be lost, of course, depends on the training objective. But for example, supposedly for this toy problem, what will be lost are the random deviations from the spiral. And that means when we reconstruct the data from the latent values back to the original space, what you see now are the blue points, which sit exactly on the spiral and are no longer randomly deviating from it. Okay? So in this sense, there is a loss of information. Okay, so if we try to formulate that, an autoencoder is simply a function made of two parts. First, an encoder f, which is just a mapping from the original space x to the latent space z, and then a decoder g, which is the reverse mapping that goes from the latent space z back to the original space x. Okay? And the goal will be to try to architecture this composite function such that the composition of G and F is close to the identity. Okay? It's close to the identity, but of course, we want also the data in the middle to be compressed. So if the goal was just for the composition to be the identity, then we could just say both F and G are the identity, so the composition of two identities is the identities. But there is no point in doing that, because of course what we want is to go through this intermediate latent space of lower dimension. Okay? And we may want to do that very aggressively. So we may want to compress, for example, high-dimensional images that would be, I don't know, 1,000-dimensional objects to just maybe a few tens of latent values. Okay, so how could we train an autoencoder? Do you have any idea? If this is our goal, we want the composition to be close to the identity. Meaning, we want the reconstruction, the values. So if we start from some vector x, so if this like this, and we map this point. No, yeah. Let's take this one maybe. We map it through the f function to a latent space. Okay, for example, there. So this is x, and this is z equal f of x. Okay. And so the goal, if the goal is for the composition to be close to the identity, it means that when I will decode this z value through the decoder G, okay, I will arrive to not x, okay, but an approximation of x, which I will denote as x tilde, which will be g of z, all right? Okay. Okay, so if these two guys, f and g, are neural networks or parametric functions that depend on parameters theta, what could be a recipe to obtain good values for the parameters theta? Yes? Mm-hmm. Okay, so that's about the that's what we'll do when we'll talk about the architecture of f and g. But let's assume that these are fixed, they are given. How do you train them? What objective function would you use to train these two components? Yes. So how would you express that? So you have a mean squared error. 1 over what? The dimension of x. Why the dimension of x? Yes. X minus what? X tilde, so it's, and X tilde is, so we go first from X to Z, that's Z, and then we decode that through G, and that gives us X tilde. Okay? So we could do that, and that's what we'll do. So we could frame this objective, and we could, so there it's over the training set, implicitly meaning that what we would actually care about is to minimize in expectation over the data from the data distribution, the reconstruction error, okay, which we can frame, for example, as the L2 norm of the difference between the input and its reconstruction. And we want this value, this expectation, to be as close as possible to 0. And if we manage to do that, it would mean that on average, for any x that we can see from the data distribution, the reconstruction would be very good, meaning the information would not be lost, at least in the sense of the L2 now. Okay, and if it's exactly 0, it means that the compression would be lossless, exact. Okay? And so if we have two parameterized mappings, two parameterized functions, f and g, with their respective parameters, then training would consist in minimizing the empirical estimate of that expectation, which is exactly the same as what you suggested. And we would fit the parameters theta f and theta g by trying to identify the parameter values that minimize this empirical estimate. Okay? And we would do that then using classical optimization algorithms that we have seen also before, like stochastic gradient descent, ADAM, or anything else. Okay? Yes? Yes? But these constraints will be imposed by the architecture, by the function f and g. Okay, so we will have a function f that, for example, let me just look at the notations I've used. PD, PND. So this x, for example, could be some Euclidean space of dimension p, very large, and f is a mapping that goes from any element from this space to another Euclidean space, but of lower dimension d. Okay, and that would be this one. Okay, and we have that P will be much larger than D by construction. Yes. And once we have made this choice, then of course the dimension of the inputs and outputs of the decoder, of the G function, they are fixed. And so G now is just a function that goes from some element from the latent space of dimension D back to some element from the original space of dimension P. Okay? And so because of this compression through the f and g function, this, what you describe, cannot happen. Okay. So what we'll talk about now are the choices that we could make for these two components, for the encoder and the decoder functions. So the first and easiest choice that we could make is to say that both the encoder and the decoder are just linear projections. Okay? And so in this case, we would say, whoops. Where is it? We would say that the encoder is made of two linear projections. Actually, the same projection, where for the encoder, we would define the projection as the multiplication of some U matrix with the input vector x, or the transpose of this U matrix. Okay, so the U matrix would be a matrix of dimension p times d, meaning when you take the transpose is a matrix of dimension d times p times a vector of dimension p. So the product of this matrix times a vector gives you a vector of dimension d. Okay, and then we could define the reverse mapping by using the matrix U directly. So we would multiply Z with U. So if Z is a vector of dimension D, which we multiply to the left by a matrix of dimension P times D, then that gives us back vectors of dimension P. Okay? Such that the composition of the two, which we need when we express the loss, is U transpose times X, that gives us an X, times U, that gives us back some X vector. Okay? And we want for this quantity to be as small as possible. Okay? And actually, this loss is exactly what you do when you derive PCA. When you do principal component analysis, this is the objective function that you will use to derive the principal vectors. Okay? Under maybe the additional assumption of orthogonality on the U matrix. Yes? What do you mean? I mean, PCA, if you keep all the dimensions, is exact. So when you do PCA, usually you will have U, the second dimension of U, to be P also. So you will have U to be a matrix of size P by P. Then you minimize this, and with orthogonality, that gives you something. And then you say you only keep the n first principal components, as we say in PCA, which is the same as just truncating directly this U matrix. And what will happen, because we have this loss, is that only the most important, only the ones that help us reconstruct the best the data will appear in the final solution, and all the remaining components that we have left out, okay, will be in this case completely discarded directly by the choices that we have made. Okay, but so just to say, an autoencoder, I mean, just to say, PCA is an autoencoder of some sort, where both the f and g functions are linear mappings, and you share the U matrix between the two. But of course, this will not work very well, because it's very unlikely that you can compress very aggressively this high-dimensional data into a lower-dimensional space using simply a linear projection. Okay? If you try to do that, a linear projection already on this 2D case, to go from the spiral to this line, with PCA, you would not be able to do that. Because you would need to unroll the spiral to determine the locations of the points on this line. And we cannot do that with a linear mapping. Okay. So, of course, the trick will be to say, well, we replace or we instantiate these two functions as neural networks. Okay? And so we'll say that both the encoder and the decoder are neural networks. And so there we have all the freedom to pick any architectures that we have seen so far, or even others. And so, for instance, we could say that both F and G are multi-layer perceptrons, where we just have to make sure we have the correct dimensions for the inputs and the outputs. So the encoder MLP would take as input vectors of dimension P and would produce as output vectors of dimension D. And we would have the opposite for the decoder, for the MLP representing the decoder. It would take now as input vectors of dimension D and would have to produce as output larger vectors of dimension P. Okay? If X correspond to images, let's say, then we could also say that both the encoder and the decoder are convolutional neural networks, for example. And so you could have the encoder being a classical CNN, which process the data with convolutional layers, would compress the data with pooling layers up to some dimension, then would produce as output a compressed version of these images, and then we would have another neural network, in this case for the decoder, which also would be convolutional and would take these lower dimensional images and would try to uncompress them back to the original space. And we could do so exactly in the same way as we, for example, architecture the UNet or segmentation networks using, for example, CNN with transpose convolutions. Okay? So let's see quickly what would happen if we were trying to learn an autoencoder, for example, on MNIST images. So if the dataset is this, so this corresponds to 28 by 28 images. So we have more than 700 dimensions for the input space. And we are trying to compress these images into two numbers. Okay, so we try to go from 700 dimensional, so from a 700 dimensional space to a two-dimensional space. In this case, the compression would be very aggressive. If you try to do that with PCA using linear projection, you would get this, and when you keep only the two first principal components. On the other hand, if you architecture the autoencoder with CNNs, even with this very aggressive compression scheme, you see that in this case the reconstruction would be much better than with PCA. Okay, so a few comments nonetheless. If you compare the reconstruction that you get with the CNN autoencoder next to the original images that we have used, you see that, of course, the reconstruction is not perfect. Okay, we don't get the same images exactly as output of the autoencoder. So, but what do you observe specifically? Can you comment? Yes. Yeah, so for example, if you look at this one and this one, 4 and 9, if you look at the reconstruction, they look quite the same. And it makes sense when you think about it, because if you look at the two digits, they only differ by one stroke. You can go from a 4 to a 9. If this is a 4, you can transform this into a 9 by just adding this. Okay, and depending on how you write, the space between the two, between these two strokes may be more or less wide. And so this is, so you can explain this artifact for this reason. What else do you observe in the reconstructions? Hmm? 5 and 3. What do you mean, 5 and 3? Where? Middle, this one? Yeah, that's correct. So this 3 has become a 5. Yeah, okay, that we've mentioned already. What about the quality of the images that you get? Yes. Mm-hmm. Yeah. Okay, they are all blurry. Why? Yeah. Yes. Yeah, but why does it get blurry? Yes.
When we write number 2,
Mm-hmm.
we will not write it exactly the same pixels
Yeah.
memory. And so by exploiting the mean of the two, what is predicted is the mean of the two.
Yeah, it's precisely because we are defining this objective as the expected value of the L2 norm. So the optimal solution for this will be actually the expected value of x. Okay, will be a mean. So if you take the mean of several images, the mean that you will get will be very blurry. What about PCA? Is it any good? So everything has been transformed either to 9, 0s, 1s, and something intermediate. And so it's not working very well. And the reconstruction are also very blurry. But this is for the same reason. It's because fundamentally PCA is based on a mean squared error objective. So what if we increase the size of the latent space from 2 to to 8 dimensions? If we do that and look at the results that we now have for the CNN-based autoencoder, we get this. And I think you would agree with me that now the quality is much better. Compared to that, the images are less blurry. They are still blurry in a sense. If you look close to the boundaries of the digits, it's still blurry, but much less than before. We get fewer of these artifacts for the reconstruction, for example, between the 4 and the 9s, which now are much better reconstructed. The 3 there, which was previously reconstructed as some kind of 5, is now correctly reconstructed as a 3. And so you see that it gets much better by just adding 6 dimensions to the latent space. If we add the same number of dimensions for the PCA autoencoder, we get these results that you see at the bottom. Is it better? Yeah, so it's obviously better, but it's still very not satisfactory, I would say. We start seeing more numbers than 9, 0, and 1s. You can see 4s, 3s, maybe a 7 there, but the reconstruction is still very poor. If we keep increasing the dimension, let's say to 32 components, now we get these results for the CNN-based autoencoder, and you see now that it's quite good. The reconstruction error, just by looking at the reconstruction, is certainly even better than before. However, if you look at PCA, it's still far from the result that you can get for the CNN-based autoencoder. However, now we have much better reconstruction. We start seeing all the digits, but we also see that there are many artifacts that still appear. You see all these gray areas in the reconstruction, indicating that we are still quite far away from the quality that we could get. And if you were to increase the dimension up to the dimension of the original data, then eventually, of course, PCA would produce correct reconstruction, because in this case, PCA could trivially recover the identity matrix. Okay. So one thing which is interesting when you consider autoencoder and basically latent space models is to try to understand how the data is transformed from the original space to the latent space. And so the one thing which is usually interesting to look at is to try to understand the structure which has been learned by the model in the latent space. So one thing that we do often in the field when we are in this regime is to look at interpolated samples, but samples that we do not interpolate in the original space, that we interpolate in the latent space. And so the idea is, for example, if you take 2 points, 2 elements in the original space, like this one there, the one that I considered before, and maybe this one there. This other point will be mapped somewhere else, maybe there, and will be decoded, if we did a good job, close to its original position. Okay? If we were directly trying to interpolate between x1 there and x2 there, what we would be doing would be to draw basically a line between these 2 points there, and we'll consider as interpolation between the 2 samples any intermediate value between the 2. Okay? But all these intermediate values, they would not make any sense, certainly, because they would not lie on the manifold of the data. However, what could happen when you interpolate not in the original space but in latent space? Now we would be mapping, so we would have Z1 for the encoded value of x1 and Z2 for the encoded value of x2. Okay, it should be like this. They are not. Okay. And now, if we interpolate linearly between Z1 and Z2, I'm not saying it works always, but we would get, for this specific example, these intermediate values that would lie on this line, such that when you decode now, for example, this one, it would not be decoded in the middle of this line in the original space. But since you decode it through the decoder itself, certainly what would happen, so if this is the spiral, like this one would be decoded, for example, somewhere there. Okay? So let's see what happens when we interpolate on the latent values first produced by PCA. So on the one hand to the left, you have the starting image. On the x1. On the right, you have x2, and you have that for 6 pairs of start and end, 6 pairs of images. And if you linearly interpolate in the projection of PCA and you decode at every step, you get these results. And so you get this transition from 1 to 7, from 2 to 7, from 5 to 3, from 0 to 2, from 1 to 2, and from 7 to 2. So what do you observe? So do you think this transformation or this interpolation, they go gradually from one image to the next? Yes, that's exactly what happens when you have linear mappings and you look at interpolated data points. What will happen is that it's as if the first one would slowly disappear, and at the same time, the other one would slowly appear. Such that at the one hand, you have only the first, which has appeared completely, and the second, which is completely off. And then you have just a linear, you have simply a weighted mean between the two. depending on the position, such that at the middle, for example, you have 50% of the first image plus 50% of the other image. You sum them, and that's the interpolated value. Okay. If you look at the interpolation in latent space for the CNN autoencoder, this is the kind of result that you get. And yeah, they are not for the same pairs of images, but that's not really important. So you would start from 0 and consider for the other image a 3, 7 to a 5, a 4 to a 2, a 7 to a 7, a 2 to a 4, and a 4 to a 7. How different are these interpolated samples from these ones? Yes. But what kind of transformations do we have now? Yeah. Yeah. It's as if the digits were slowly deformed, stretched, and modified to go from one to the other. And what is interesting is also to notice that maybe not everywhere, but the interpolated values, they still represent digits or images that we can recognize as digits, except maybe in the middle where it's maybe more difficult to assess. But here, everything in the middle is or even close to the boundaries is, yeah, it's not of the same quality. If you, for example, look at how you go from this 7 to this 7, all the intermediate images are clearly 7s. Okay? Okay, so this is about compression which you can achieve with an autoencoder. Another interesting application of autoencoder is what we call denoising autoencoder, which would be the case where you know that in your input data there is noise, and you would like to remove this noise. You would like to clean, in a sense, the input data. Okay? And so let's say you have let me check. Yeah, let's say you have pairs of noisy data and clean data. Okay, you can train, in this case, something very close to the autoencoder, except that in this objective, you would use, on the one hand, the noisy data, and you would try for the autoencoder to reproduce as output the clean data that you have, that you know. Okay? So if you are in this setting, you can train this autoencoder, which in this case we call a denoising autoencoder. And so the goal is for the composition of the two parts to be close to the clean data. And so if you do that, for example, on this toy example, where we would have, for example, clean data which would lie on this curve, on this manifold, but the only noisy data that we have are located around it. Then what the denoising autoencoder would learn is how to remove the noise, or the noise that should be removed, to basically reproject the data on the clean data manifold. Okay? And so, just to give you an example, or a few examples on maybe something more concrete, like images. If you have, for example, corrupted images, where you have removed or masked out some of the pixels, because, I don't know, for example, instrumental noise, your camera is not working perfectly, but you have a training set like this of masked pixels for some of the you have a training set where some of the pixels are maxed out and randomly masked out. Then you can train this denoising autoencoder such that from these images you try to reproduce this one. Okay? And if you look at the reconstruction, this is the kind of reconstruction you would then be able to do starting from this image, and you would be able to reproduce these other images. Okay? Where now the goal of the decoder would be to try to basically fill in all the pixels that were missing before. And that can work surprisingly well, even if you have a lot of corruption. So if you increase the corruption and say you only observe 10% of the pixels, or you have removed 90% of the pixel, it is still enough, at least in the case of MNIST, to make meaningful reconstructions. And you can use, for example, the same strategy for other kind of corruption processes, like to go from a blurry image to a crisp image. Let's say you have a Gaussian blur with a very large variance of 4, and so this corresponds to your corrupted data, for which you want to remove the blur. You can do that again using the same denoising autoencoder strategy, and this would be the kind of reconstructions you would be able to obtain. There is, however, a very major weakness to denoising autoencoder is that the output of the architecture is just one single value, and this one single value would correspond to the expected value of the X image given a noisy image X tilde in this case. Okay? Meaning, if we take this in reverse, if the posterior distribution of clean images given some noisy images is multimodal, if we approximate this posterior distribution with just one number, and this is what we would do if we architecture the autoencoder in this way, the G function would just produce one reconstruction and only one. And if we say that we train it by minimizing the L2 norm, then the solution would correspond to the expected value of the posterior, so the expected value of some clean image of the clean image given X tilde. But but the main problem with this is that this expectation may not be a plausible sample. This expectation may not be something which is plausible under the data distribution. Okay? So, for example, if the data distribution is multimodal like this, with two modes, and then minimize the L2 norm, we would obtain something close to the expected value. But you see that the expected value, in this case, it's very unlikely. It's in neither of the two modes. So it would produce something in between, but which is not plausible in itself. Okay? And this is why, maybe not there, but for this one, you start seeing that. You start seeing there intermediate reconstructions that are, in a sense, blurry, but also have artifacts like this. And this is a result of this multimodality, which we do not capture by producing point estimates as output. Okay, so we have this autoencoder now, or a denoising autoencoder, but the goal of today was to try to build a generative model of the data. So do you see a way, if I go back there, or maybe just there. So given this architecture, do you see a way that maybe you could try to be able to generate data, so X values, given the architecture that we have? Or could we adapt the autoencoder to be able to generate data? Because so far the autoencoder need data as input that we encode and then decode. Yes, or you? Yeah. Yeah. So we could have so this is X. Then we map this to Z. Then we have the decoder G. And so you say we associate to Z a probability distribution. Okay, that's more or less your idea. So we could say, for example, very simply, I don't know, that we put a Gaussian distribution, maybe there, on these values. And once we have that, what do we do? Okay, so now if the goal is to implement a sampler of data such that we would implement this, we could do so by first sampling some Z value, right? So we could sample, and if this is a Gaussian, we could say that, okay, we sample from some Gaussian distribution, and then we decode the values that we generate from this Gaussian and say that X is equal to G of Z. Okay, but there is a big issue with that. So this Gaussian distribution, of course, depends on two parameters, a mean and a variance. Okay, but how do we fit these parameters? Yeah. By sampling what? So you with a string set X, yes. And then? So we could do something like this. It's exactly the same schema, but for Z of dimension 2. And so we could say we associate to the latent space a Gaussian distribution, okay, from which we generate Z vectors, and we decode to produce values in the original space. But we have the same problem. How do you pick good values for mu and the covariance matrix? Yes. Okay, but let's do that. If we do maximum likelihood estimation, what would be the values for mu and sigma? Yeah. So what we could do very naively, but that would not be wrong, would be to take the input data set, to encode it through the f functions. Now we have a data set of latent vectors of these, for which we compute the empirical mean. So we take the average of all these vectors, that gives us a vector, and we use this vector for mu. That's the empirical mean. of the latent vectors, and we can do the same to estimate the covariance matrix. Okay, and so we plug in these two quantities into this normal distribution that produce z vectors as output. Then we decode them through the decoder, and that produce x values. Okay, so we would do that like this. If then you look at the samples you would get out of this model, this is the kind of results you would obtain. So for a latent dimension of size 8, we would get this kind of results. And if we increase the dimension of the latent space to 16 and 32, you would get this other kind of results. What do you think? So, would you be happy to see these kind of results from your project? Okay, so it does not work. Okay, it's a quite wrong strategy actually, because actually we are trying to solve the same original problem as before. So we are trying now, instead of directly having a distribution in the original space Px, what we really need now is a distribution over some outer space, the latent space Z, but fundamentally, mathematically, it's still the same problem of learning a distribution over some space. Okay? And so, of course, if we say that this distribution is Gaussian, then it's very likely that by magic, the vectors that we learn, that we obtain by the autoencoder are Gaussian distributed. There is nothing like this in the autoencoder architecture. We never say explicitly these vectors that you have in the middle, they should follow Gaussian distribution. We just say they should lead to a good reconstruction error. So this choice obviously is wrong. This distribution is too simple with respect to the actual distribution of the z vectors. Okay? Okay, so the results are not very satisfactory because the density model, the Gaussian distribution on the latent space, is too simple and fundamentally inadequate. And building a good model in latent space basically amounts to our original problem of modeling an empirical distribution, except that now this empirical distribution is no longer on x vectors, but on z vectors. Okay, so we have not really solved the problem or made any improvement yet. Okay, we can compress data, but we can't. We are still not able to generate any data meaningfully. Questions? Okay, then let's take a break and then we'll continue with VAEs. We'll resume at, let's say, 10. Okay. Okay, continue. Okay, so far we talked about autoencoders, and you can use them, and they are quite useful for many applications, but basically you can use them to learn how to compress the data without losing that much information. But if you want to use them to generate data in the first place, they are still not solving any problem, because if we associate to the latent space a data distribution, we are back to the problem of trying to learn a distribution of some data, even though now this data is latent, it's still data, and so we have not solved any problem. So what I will do now is to derive with you the variational autoencoder. So I will we'll start from variational inference, which we've already used last time, and which will apply to the structure of a latent variable model that goes from some latent space equipped with some distribution to the data space that we want to model. Okay? So the first thing, and I will do this mostly on the blackboard to make sure you all follow and it's not going too fast. So we'll assume a latent variable model, the simplest we can, which is just a latent variable model made of two variables. First, some latent variable z, and the data variable x. Okay? And we'll assume, or we'll factorize this distribution in this way by saying that we define the latent variable model by first defining a prior distribution pz over the latent. Okay, so we have pz where the z's are so we used the letter D, so let's use this one. And for x, we have that x are vectors of dimension p. Okay? And we'll say that, okay, we also have a prescribed, and for now we'll say that it's prescribed, it's given probabilistic model that relates x conditionally on z. Okay, and this conditional distribution will come with some parameters theta. Okay, so in a sense, this is just a very simple Bayesian network, if you remember that from Intro to AI, where we have two variables, z and x, such that together, these two things gives us a description of the joint probability distribution of the two variables, so of z and x, through the factorization of first the prior times the conditional px given z. Okay? And the parameters, they will only enter inside the conditional distribution, and we'll assume that the prior distribution is something simple without any parameter. Okay? Now the question, if we are in this setting, of course, is how to fit the parameters. How would you do that? So, given that you have access to a data set of X, Z, of course, you don't observe, it's something that we make up. They do not exist. The only thing that exists are realizations X that we have in the training set. But we still have a probabilistic model over these X elements. And this probabilistic model depends on parameters theta that, of course, you would like to fit. So how do we do that? So what have we done in the past when we consider other kinds of probabilistic models that depended on parameters and we had access to data? How did we fit the parameters theta? Or the weights or anything else? Yes, so we just do that. We want to do maximal, so we could use maximal likelihood estimation to obtain values of theta which maximize the likelihood. Okay? So, in this case, the likelihood that we have, or the problem that we could frame, is to maximize with respect to theta, well, the likelihood of the data, and the data is only about x. Okay, so in this case, more precisely, what we will do is to try to maximize the marginal likelihood of the data x. Okay, and what is the marginal density of x under our model? How do we go from this joint to the marginal distribution over x? Yes? You integrate over? Exactly. So this is the integral over the z's that each come with a prior density pz of the conditional density of x, which depends on parameters theta, given these z's, okay, and we integrate over the entire latent space, so times dz. Okay, so this integral, you can rewrite it using another notation, which is simply as an expectation. Okay, the integral is the same as the expectation over the pz distribution of this conditional density p of x given z, right? Okay, so now how do we, if this is the expression, the quantity that we want to maximize, how do we do that in practice? Yes. Yes, so the issue is that we don't have a direct access to the expectation, but we can use the training data to estimate this expectation. And so in this case, we can say that we can sample a certain number of z vectors from the prior, and then build an empirical estimate, in this case the empirical average of the expectation of the conditional densities, and that will approximate the expectation. Okay, so this is not equal, but only approximately equal to, let's say, 1 over k of the conditional density of x given zk, okay, where each zk has been sampled from the prior. Okay? So we could say this is our training objective. So we'll build these empirical averages, and then we'll do, for example, gradient ascent on this quantity to update parameters theta until we reach some maximum. Okay, if you try to do that, that will not work at all. And the fundamental reason is that it's very so the reason is that this estimator actually comes with a huge variance. So it's unbiased with respect to this quantity, but the variance of the estimator is very large. And so in practice, it will not be very useful. And intuitively, the reason is that if you sample blindly z vectors from the prior, it's very unlikely that these random z vectors that you have drawn without looking at the axis will happen actually to explain the data that you have quite well. So you will be certainly in the regime where the z's that you have drawn from the prior will be such that the axis that you are given in the training set will be unlikely, And so depending on the choice that you make for the conditional, let's say a Gaussian, then you will be in the tails of the Gaussian, for which there will be, you will not have any density, and the gradients will be flat. So you will be stuck. So this is nice, but in practice, it does not work. Poor approximation. And this problem becomes even worse as the size of D becomes larger and larger. When D is... Okay, so we have to do something else. And the thing that we'll do instead is called variational inference. And the trick of variational inference is to still try to maximize this quantity, this expectation, but using a better estimator. Okay? So we know that P of X is this expectation over Pz of the conditional. Okay. And in variation, so basically the main issue with the previous approach is the fact that we draw these z's blindly without looking at the axis. And that's the reason why many of these z's, they fail to explain the axis. So one trick would be to say, what if instead of using this Monte Carlo estimator, I change the sampling distribution of the z's to only sample z values that should explain already well this axis. Okay? So the trick of variational inference will be simply to swap the sampling distribution. And you can do so without actually changing the objective. You could say that this expectation is equal to the expectation of the same quantity, but picking another distribution from which you get the z values, and we'll call this distribution Q. And this is what we call the variational distribution. This distribution will come with parameters also, phi. Okay, so I'm just swapping the sampling distribution Pz, the prior, by something else. And for this equality to be true, okay, I need, of course, to account for the fact that now I'm no longer sampling from the prior, but from something else. Okay, so I should do a correction which is proportional to the prior density and inversely proportional to the sampling distribution. Okay, of the same quantity for which I want to compute the expectation of. Okay, and this step is what we call important sampling. Okay, so this is nice, but if you paid attention, I was trying to optimize parameters data, and now I'm making the problem more complicated by adding another distribution which also depends on parameters. So now I have two sets of parameters to optimize. Okay, but fair enough. We'll see that this is not really a problem. Okay. Okay, so how do we go and move forward from there? So what will maximize is not directly the density, but the log of the density. Okay, so I can rewrite this by taking the log of the two sides. Okay, and have the log of the expectation over Q of that quantity. Okay. Now there is still a so okay, I can do that. Fine. But now we have the logarithm of an expectation. We have the logarithm of a big sum. That's not very nice. What we can do, however, is to define a lower bound on this quantity using Jensen's inequality. And through that, we'll be able to put the logarithm inside the expectation. Okay? So I can define a lower bound on this quantity using what we call Jensen's inequality. Okay. So this logarithm is a concave function. So we have this relation, and that allows us to rewrite the log of the expectation as the expectation of the log. Of logarithm now of PZ Q Z Px and now this is nice because this logarithm of a product can be exploded into a sum of logs. And we can pull out the logarithm of this. So we would have the expectation over Q of Z of the logarithm of the conditional density of the data X given Z. And then here we have the expectation over Q of the log of P over Q. That should remind you of some quantity. This is the negative KL between Q and P, between the sampling distribution and the prior. Minus KL. Okay, so this quantity that we have there is what we call the elbow. It means the evidence lower bound. The evidence is this guy, P of X, the marginal density of the data. That's the E, and it's a lower bound because we have this inequality, and the O means objective. Okay? So instead of maximizing the log of the marginal density, we'll be maximizing a lower bound on that quantity, which is the elbow. Okay? And the elbow, you can rewrite it in this way, which is nice for interpretation. You see two terms. You see the expectation of the log of the conditional densities. This is the reconstruction error, but now in the sense of the likelihood that we assume. If you say, for example, that P of X given Z follows a Gaussian distribution, then this will reduce to a squared error, exactly as we did before when training an autoencoder. But now, at the same time, we are also saying we should sample Q values such that they remain close from some prior, PZ, that we have chosen. Okay, and this will be what I will call one. Okay, and now if we start from the same elbow objective, log BZ Q. Okay, I'm just rewriting this, and I will derive another expression for it. Okay, so inside the expectation, okay, what I can do, and I suppose you will agree with me, I can multiply by 1. It will not change the expectation. Okay, and I'm defining 1 as the ratio of the marginal densities with itself. Okay, so okay, and then the trick. So there, now in this expression, you should recognize Bayes' theorem. Do you? So if you combine this, the prior times the likelihood over the evidence, that's the posterior. So you can rewrite these 3 terms in terms of a posterior. Log of the posterior, P of Z, not X, given X, not Z, and that depends also on the parameters, over QZ times PX. Okay, now that we have this, we can rewrite the log of this product as a sum of logs. And so the sum of the log of this ratio and the log of the evidence. And you see that X, this quantity, does not depend on Z. So we can also pull it out completely out of the expectation. And so we have log of P of X plus the expectation over Q of the log of P over Q. Again, this is a KL divergence, but not the same. Now it's a divergence. And it's the negative divergence between Q and the posterior. And this is 2. No, in orange. Okay, so we have derived the elbow in 2 different ways. We arrived to the fact that the elbow is equal to this expression, and that the elbow at the same time is equal to this expression. Okay, so 1 and 2 are equal. So if we combine the two and reshuffle the terms, we have that the logarithm of the marginal density is equal minus the KL is equal to the elbow. And if we put this other term in the other part of the equation, we arrive to the fact that the logarithm of the marginal density, which was our initial objective, can be re-expressed as the elbow, which depends on data and parameters, with two sets of parameters, the ones for the conditional distribution and the other one for the variational distribution. So this is this term, plus now the KL divergence between Q and the posterior. Questions so far? So what does that mean? So let's say the x-axis corresponds to the parameters and the y-axis corresponds to the objective. So we could have, on the one hand, maybe something like this, which would correspond to the logarithm of the marginal density. So this term, the actual objective. But of course, we can't directly maximize this. So what we've done is to re-express this in terms of these two terms. And what I suggested was to at least maximize the lower bound on this quantity. And the lower bound is given by the elbow. Because this other term, I don't have access to it either, because I don't know the posterior. Okay, but so what we have is something maybe which will be like this. So that will be the elbow as a function of x and the parameters theta and phi. Okay. And okay, where is the maximum? So the best parameters theta, they are these ones, the ones that maximize the log marginal density. Okay, so this is theta star, the one that we would like to identify. And if I set the value and I freeze the value of phi, the parameters of the Q distribution, the sampling distribution, we would now have something like this as a function of theta. The other two are fixed. Okay. And now if we maximize the elbow with respect to theta, it would arrive to this value instead. Okay. And you see that the gap that we have between the two the gap that we have between the two is something that we know. It's this guy. Okay, so how should you interpret that? It means that, okay, we know that if we maximize the elbow, we'll be making a mistake, and the mistake will be proportional to the difference between the two curves, okay, or will be related to this gap between the two. If we could shrink this gap to 0, Okay, certainly that would be better. But in order to do that, you would need to know this posterior. Okay? Or another way to say this is to say that the best sampling distribution we should pick is the posterior distribution over the z's, given x. Okay, because in this case, the gap would be equal to 0, so this term would be equal to 0, and the elbow would be equal to the actual objective. Questions? Okay, so this is what we would do if we had only one x. But we have several in our training set. Okay? The choice of the sampling distribution, you see, does not depend on x anywhere there. I've just said, okay, we will pick some other sampling distribution over these, but never ever you see x entering this sampling distribution. Because indeed, in everything that I've done so far, x is supposed to be fixed. We have one x, and then for this specific x, we'll try to obtain a good or a better sampling distribution over the z's. Okay? But of course, we have several x's, so that means certainly we should condition this sampling distribution over z's to the x's that we have. Okay? And so if we do that, we arrive to the third part, which is what we call amortized inference. Okay, where basically we'll go from Q, some sampling distribution over these, and now we'll upgrade this to a sampling distribution over these, as before, but now conditionally on some x. Okay. And now what we have is what we call a variational autoencoder. Why? So where is the autoencoder in this development? So you see that we have two parts now. We have this distribution. You start from z, then you define a conditional distribution over the axis, conditionally on this z. Okay? So basically you decode some z into a distribution over x. Okay? So it's almost the same as before, except that instead of mapping a z to another x, so one z to one x, what we do now is we map one z to a distribution over x's. Okay? But we are still effectively decoding z, but now to a distribution. Okay? So this is the decoder. And the sampling distribution, well, you can interpret it as an encoder, which would take an input, a data vector as input, and would produce as output a distribution over the z's. So the encoder is no longer mapping one x to one z, but one x to a distribution over z's. Okay? And so this is where you have the autoencoder part of the variational autoencoder, and we say it's variational because this because we use variational inference and everything are distributions, and this encoder is the equivalent of the variational distribution, the sampling distribution that we have when we do variational inference. Okay, so can I erase everything from this one? Okay, so let's start with the encoder. So the encoder is this QZ given X, which depends on parameters. And what we'll do, of course, is to instantiate this variational distribution as a neural network. Okay? So we'll have some neural network with whatever we want inside. Okay? But this neural network takes as input some X vector. And what we want, also it depends on parameters, the phi parameters, and should produce as output a distribution over these. How would you do that? How do you make a neural network to produce a distribution at its output? Yeah. Yeah, so you could make a choice. So we are dealing with this, QZ given X. And so you could make a modeling assumption and say, for example, that this follows a Gaussian distribution over these, but that depends on two parameters, okay, a mean and a variance or covariance, and we can just say these are functions of the data, okay? And we'll say that these two parameters are produced by a neural network, and so these two quantities will be the output of the neural network. And of course, you could make other choices for the sampling distribution, for the variational distribution. If you have good reasons, you can pick something else than a Gaussian. And so we could similarly have the variance or the log variance if you want to avoid numerical problems, as we discussed last time. And once we have these parameters, you can say this will enter a normal density that you can evaluate at any z, and that will produce, at the end, the density that we interpret as QZ given X. Okay? And now we can also define the decoder, which is really the mirror of this architecture. And so similarly, we could say that P of X given Z is Gaussian, but again, we could make other choices over X given mu Z and some covariance Z. Okay, and so we would have a neural network, the decoder, that takes as input a Z vector, and then produces as output a distribution over the axis. And again, we can just say the output of the neural network will be parameters of this distribution. So mu Z and again the log variance of Z. Okay. And we can feed that in a Gaussian distribution, which we can evaluate at any x to produce what we call the conditional distribution of x given z. Okay, so now we have two networks, and we want to train them. How do we do that? Yeah. So we have the first network, which depends on phi, and this one depends on theta. How do we optimize phi and theta? What loss function will we use? Yeah, that's the objective that we've derived. So I've tried to show you that we can't directly evaluate the log marginal density. Instead, we'll maximize this upper bound, the elbow. Okay? And so we have the elbow, given that takes as input some x, and the parameters of the two distributions, so theta and phi. Okay? But the elbow is something that we've derived for one x. So what we'll do instead is to maximize the elbow in expectations over the axis. Okay? And the objective will be to maximize this with respect to our parameters jointly, so theta and phi. Okay, and so if I now just rewrite once again the elbow, but now inside the expectation, we have the expectation over px of the expectation over the sampling distribution phi, q phi of z given x, the one that we sampled there from the data distribution. Okay, so there is no theta there. It's not a mistake. It's because we sampled from the actual target distribution. So now we sample conditionally z is given x, and then we compute the expectation of the logarithm of p of x given z. And now there is a theta because this is our model. Minus dkl between q phi z and the prior. Okay, so how should you interpret this objective? It says that we'll be trying to maximize the marginal density of the data, which we decompose in two terms. We'll say that we'll try to maximize how well the training data is explained by our generative model. Okay, this is the reconstruction error. This is how well the model explains the data. And at the same time, we'll try for the sampling distribution. So for the z's that, oh, sorry, there is one mistake. We'll also impose that at the same time, the posterior distribution, so the sampling distribution should remain close to the prior. Okay? And so you should see there that there is some kind of contradiction because because of this negative KL penalty, the sampling distribution should remain close to the prior. But at the same time, if really we want to maximize the logarithm of the marginal densities, which we have written also in this term, I've told you that the best choice for QZ given X should be the posterior. And so QZ given X cannot be the posterior and the prior at once. And that's a big problem in VAEs, which I will talk about next week. We'll try to resolve. But this is one of the main issues of VAEs. Because of this tension between these two opposite objectives, we will get issues to get satisfactory results. Okay, but other than that, basically the intuition, we design the VAE such that it produces a conditional data distribution which explains the data well. Okay. And vice versa, we design the encoding distribution. So when X is fixed, we design a sampling distribution for the Z's such that these Z's, they explain the data well. Okay, so we have these two things. We want Z's that explain the data well, and we want X's that are well explained by the Z's that we generate. Okay, we want the two things together. Okay, so in the slides you have all of this as well. So I will just flash through them. So we start from the latent variable model, which you can see as a generator. You start from Z latent variables and all together define some X values. How to fit the latent variable model, we do maximum likelihood estimation, but this does not work very well because the expectation, the empirical average is not a good estimator of the expectation. We do instead variational inference, from which we derive the elbow objective, which we can rewrite in two ways to arrive to that equation, which you can interpret in this way. And to optimize, we would want to optimize jointly the two set of parameters and maximize the elbow. Okay. Now there is still one practical issue. So again, practically we'll not be able to evaluate this expectation exactly, but we can do a Monte Carlo estimate of the expectation by using samples from the training sets, which are samples from the data distribution, and then forming a Monte Carlo estimate of the expectation. Okay? And then we have this. But then what will happen is that at some point we'll need access to the gradient of the elbow with respect to some X for theta and phi. Okay, but we want to update the two set of parameters. So we'll need the gradient of the elbow with respect to theta, but also we'll need the gradient with respect to the phi parameters of the elbow. Okay. And the issue is this inner part, because I mean, for this one there is no problem. We can form also, for example, a Monte Carlo estimate of the inner expectation by sampling from Q Z vectors and then evaluating the empirical average of the logarithm of the conditional densities. However, for this one, that does not work because the gradient of this expectation will not be equal to the expectation of the gradients. Why? Because the phi parameters, they affect the sampling itself. Okay, so you should account for, if you have the gradient of an expectation, it's not the same as the expectation of the gradients if the parameters affect how you sample from that distribution on which you compute the expectation. Okay, so I will just, it's there later. Okay, I will go back quickly to this. It's a bit secondary, so it's not that important. But so for the variational autoencoder, we have something like this now. We have there on the slide, and I can maybe put the other one back. So we have the encoder that goes from one X vector to a distribution over these. And then what we'll do during training is to maybe produce realizations of Z vectors out of this sampling distribution. And these Z vectors will enter the decoder, which itself will produce a distribution conditionally on Z on data vectors X. Okay? And so you can instantiate all these components. You can say that the prior, for example, is Gaussian. You can say that the likelihood, so P of X given Z, is also Gaussian and parameterized by a neural network. It's exactly as I did there. And you can do the same for the sampling distribution or the posterior QZ given X. Okay. Then we arrive to this objective, as I derived there. And then this is what I was about to say. Then to maximize this objective, we need to differentiate through it to obtain the gradients. Okay. So for this one, for the gradient of the elbow with respect to theta, okay, so if we do everything, we just rewrite the elbow in this way. So this is the same as before. It's just this is expressed in terms of the joint, but if you factorize the joint as the prior times the conditional, and then you put back the negative of the log as a ratio, you recover the previous expressions. And so what we have, importantly, is that the gradient of the expectation of this expression, in this case, is equal to the expectation of the gradient of the expectation. Okay? And then everything simplifies, and you get that the gradient of the elbow with respect to theta is the expectation over QZ of the gradient of the reconstruction error or the log likelihood. Okay? And this thing can itself be estimated by Monte Carlo. Okay, you sample these from the encoder, and then you say that you approximate the expectation as the empirical average of the gradients that you compute now for one X and one Z. However, for the other gradient, the gradient of the elbow with respect to the phi parameters, the parameters of the posterior slash encoder, we have that this is equal to the gradient of the expectation. So that's the same equation there, except that we have the gradient with respect to phi instead of theta. And you cannot simply, in this case, say that it is equal to the expectation of the gradients. Why? Because you see that phi, that the expectation itself is a function, the way you sample the distribution is affected by the parameters. So how do we solve this problem? Any idea? So fundamentally, if we look back at what happens in terms of a graph of computation, this is the objective, which I will rewrite simply as some function f, which depends on x, z, and phi. Okay. And if we want to update phi, we need to traverse backward this graph of computation to compute the gradients. But in the middle, we have this z, okay, which we have produced by this sampling distribution, and this z, they depend, even only randomly, on the parameters theta. Okay, so because this node is stochastic, it's not a deterministic function of its input, we cannot just backpropagate through it. Okay, how do we solve this problem? Well, the trick is what we call the reparametrization trick. and is to say that we'll re-express z as a deterministic function of phi, x, and some random quantity. Okay? And so, for example, we can say that z is a deterministic function, it's the output of some deterministic function g which depends on theta, x, and some random quantity, let's call it epsilon. And what is important is to design this random quantity as a random variable which does not depend on neither phi or x. And if we do that, then we arrive to this new graph of computation in which z, okay, because we have re-expressed it as this deterministic function, which will depend on these three quantities, but now we can backpropagate from f through z to phi. And we don't have to traverse this some random node anymore. And the way we can do that, if we make the choice that qz given x follows a Gaussian distribution, okay, of some mean given by the output of the encoder, the first output of the encoder, and variance the second output, well, we can just say that we will be sampling first some epsilon quantity from a Gaussian distribution of zero mean and unit variance. Does not depend on x and phi. And then, from this epsilon, we rescale epsilon by the standard deviation, so sigma of x given the phi parameters, and we offset by the mean produced by the neural network. Okay? And so through this parameterization now, we can now backpropagate. Okay? So given the change of variable, mathematically, what we would be doing is to rewrite the gradient of the elbow with respect to phi as the gradient with respect to phi of the expectation, but now taken over P of epsilon, a distribution over the epsilons, instead of a distribution over the z's conditionally on x and the parameters. Okay, and because of that, now the sampling distribution for the expectation does not depend anymore on the phi parameters, and you can insert the gradient inside the expectation and re-express now the gradient of the elbow as the expectation of gradients. Okay, which again, now we can Monte Carlo estimate. Okay? Do you have questions on this, on the mathematical derivations of all these parts? Yes? But because they are this, I mean, we do them effectively in PyTorch. Everything would happen at the same time, but they do not affect the same elements. So when you, and this is what actually I will do, when I implement an actual autoencoder, I will have a set of parameters, and the set of parameters will correspond to the union of theta and phi. Okay? But for this to be able to backpropagate, you need to have rewritten at least the objective function through the reparameterization trick. Yes? Because I don't have access to the. That's a good. So we have elbow plus KL. No. Plus KL of Q. Q of Z given X and the posterior PZ given X. Okay? And so, yeah, you are correct. Why don't we also maximize this quantity? Okay, the issue is that this KL, okay, so this term there is equal to the expectation over QZX of the log ratio of QZX and the posterior. Okay? So that I can sample from, that I can evaluate. That's the output of my encoder, but I need to be able to evaluate this quantity. Right? But PZ given X, because of the base rule, so I don't have a direct form for this one. However, I can use the base rule and re-express it as P of X given Z over, right? That I can evaluate, but we are back to the same problem. I need to be able to evaluate the marginal density. Okay? So because of the exact reason we couldn't evaluate the marginal density, we can't evaluate either the posterior. Okay? Because for the posterior, you need the marginal density. And actually, if we had access to the posterior, well, we would not have any encoder at all. We would just be using the posterior itself as the encoder. And if you do that, what you get is expectation maximization, actually. Okay, let's maybe take a break and resume in 10 minutes at 11:15. Okay, so now to understand VAEs maybe from a more practical point of view, I will show you how to implement it, given all the components that we have defined, given the objective function that we have derived. And I will do so I will try to train a VAE directly on images. This will be very simple images, like in this case, the MNIST images, like in the examples from the slides. So this is the data that we have. We have images of digits of size 28 by 28 pixels, grayscale, and we have the usual variations of the digits. So we have 10 possible digits, but the way they are written, of course, changes from one image to the other. Okay, so the VAE, it's only that. Is it? Okay, maybe I'll do this. It's 20 lines of code, and I will do something very simple in this case. So I need to define the encoder and the decoder architectures. Just for the presentation here, I'm considering MLPs, and so I define them as sequential, as a sequence of layers: linear, ReLU, and then linear at the end. You see that I go from 784 to 100 dimensions, which I maintain until the end. But at the very last layer, the output layer, I project to the dimension of the latent space, in this case, which I set to 32, times 2. Why times 2? Can you tell me? Exactly, because I need 2 parameters per component in the latent space, okay, a mean and a variance. Okay, so that's why I have these 2. And the decoder is the mirror of the encoder. I start now from a vector in the latent space, and the dimension of this vector is the size of the latent, and it's not 2 times the latent. In this case, it's really the size of the latent, because we are dealing with instances of the z's, not parameters of the distributions of the z's. Then ReLU, linear, and then a sigmoid activation at the end. And so here I'm making a choice which is slightly different from from what I did there, where for the decoder, there in the slides, I make the choice of a Gaussian distribution, but of course I can make other choices. And so in the code, I'm making a different choice. I'm saying that the pixels, they take binary values, 0 or 255 or 0 or 1, and they follow a Bernoulli distribution of a parameter P, which is given by the output, in this case of the decoder. Okay, and this parameter should be a probability value, so some number between 0 and 1, and that's why I use a sigmoid there, because I know that the output of the sigmoid will be a quantity between 0 and 1, which I can then interpret as the parameter of that Bernoulli distribution. Okay? And you will see that that will also have an effect on the elbow. Do I have it somewhere? Of course. Ah, yeah, it's there. But I will come to that later. So I have these two architectures, and then I define the forward activation as a complete loop that goes from data to a random from data to QZ given X. Then I sample some Z from that distribution, and then I decode it back. So I then evaluate P of X given Z, the Z that I've sampled. Okay, so in code, I start from some X as input, then I pass it to the encoder architecture, and that gives me a batch of parameters which I reshape as a tensor of size, batch size 2, because I have two parameters, and then the number of latent dimensions. Then I extract out the mean parameter as the component 0 of the second dimension of this variable, of this tensor, and the log variance as the other part, the second half of this tensor. Then I sample a Z, and I do that through this reparameterization trick. So I actually sample an epsilon following a Gaussian distribution, and I need as many components. I need a dimension which is the same as the latent space. So in this case, this is given by the shape of mu. The shape of mu. I put that on the device, and then from this I create the Z value. And so I need to rescale by the standard deviation, but I don't have directly the standard deviation. I have the log of the variance. So I exponentiate the log variance that gives me the variance, and then I take the square root of that. That gives me the standard deviation, and I multiply this quantity with epsilon, and I will have rescaled now the variance of this epsilon random variable. And then I shift the location of this random variable by mu to obtain the mean, the target mean that I want. And then I return all these intermediate quantities. I return mu, the log variance, the Z, and then the output of the decoder, which in this case will be the output of the sigmoid. So in this case, the parameter of the Bernoulli distribution. Okay, and then I have a training loop. So I will be iterating over my data loader, and then I will be maximizing the elbow. Okay, which I re-express as the expectation over the epsilon distribution of the log conditional density of the data given Z, which is itself expressed as this function of epsilon and X. Okay, minus the KL penalty between the sampling distribution, so the encoder distribution QZ given X, and the prior. Okay, so I reset the gradients, I do a forward pass through the VAE, and that will call this code. I will get now access to all these quantities. And now I have to evaluate these two terms, so the reconstruction and the negative of the KL penalty. If we say that this follows a Bernoulli distribution, this whole thing will simplify to the cross entropy. Okay, it's just a classification problem now. You should produce values that are either 0 or 1. The pixel is on or off. Okay, So you have to predict a category, and you do that with your conditional model, which takes as input some z and produce some x. Okay, but this is just a classifier in a sense. And then you want the output of this classifier to be consistent with the labels that you have, and that's why you have the cross entropy. Okay, so we do this reduced to the binary cross entropy, and we pass on the probability estimate x hat, so which corresponds to the output of the encoder, of the decoder, sorry, which we compare to the actual pixel values x. Okay, and then we do that over the entire image, and we reduce everything by just summing over the image and then taking the mean over the batch. To that, we have to add the negative KL, okay? But since also we have to express this thing as an objective which will minimize, okay, so the elbow is a quantity that we want to maximize, but in PyTorch we have to pass functions that will minimize, okay? So in this case, that will become minus the expectation plus the KL, and in this case the KL corresponds to this, which in this case is you can evaluate analytically. Why? Because we make assumptions. We say that PZ follows a Gaussian distribution. We say that QZ given X, so this guy there, it's actually really a Gaussian distribution. That's a choice that we make. And the KL divergence of two normal distributions is known, is a quantity that you can evaluate analytically. Okay? And this gives us this expression there. Okay, so we add this to the loss, then we backpropagate, and we make a step. Okay, and then we iterate over the batches. Then I have some bit of code to evaluate the quality on some test sets. So I will simply evaluate the test loss, so the elbow on some test data. And I will also, as I train, look at realizations that I get out of the generative model. Or no, in this case, these are reconstructions. All right. So if we train this, and I will train this for 10 epochs over the entire training set of MNIST. So at the very beginning, so this every time shows you 5 random samples from the test set and their reconstructions. So of course, before any training, it's producing random pixels. And then after one iteration, we get these results. And then we'll wait for the training to happen. So hopefully we see that at every step, the training objectives, so the elbow, decrease. And so some are well reconstructed, others not really. So of course here the quality depends on many factors. One of them is simply the dimension of the latent space. I've set it to 32. And second, which is tied also to how well we will perform, is the architecture of both the encoder and the decoder. And in this case, I'm using MLPs, which are certainly not the most adequate when it comes to generate and process images. But so these are the final results after 10 epochs. They are okay, but not great. But still, it works to some extent. If we add reduce the size of the latent space, maybe I don't know, to 4 components. So now it should be even more difficult for the VAEs to work well. And again, you see this kind of mistakes where 5 and 3s seems to be entangled together in the latent space, and a 5 can be decoded back to a 3, and certainly vice versa. So is any of you working on a generative model for the project? No? I mean, 1, yeah, 2. And what architecture do you use? Okay, on images then. Okay. So here it's not working very well for this very reason. I hope that you get better results than these ones. Okay, so you get more or less the idea, and now, because that was the point of this whole lecture, can we really use that to generate data? And so let's see. So what I will do is that I will generate data from the prior. I will sample z vectors from the prior, and then I will decode this data from through the decoder to produce realizations X. Okay, and these are outputs that we get. Okay, we can recognize digits. Yeah, it's not that great. And again, the reason is due to the decoder. In this case, I've trained on only 4 components. So it's a very small latent space. And also, and this is maybe less obvious, okay, so we try to maximize this, the elbow. But when we generate, we are not sampling the z's from the encoder. We are sampling the z's from the prior. And this is precisely the reason why we should have this term. Because at sampling time, we want the z's that we get to explain the data well. Okay, but we'll be sampling from the prior. Okay, so another way to say that is if the encoder was not close to the prior, then at sampling time, we would be sampling these that are very far from the ones we have used at training to explain the data. And so the quality of the generation in this case would be very poor because we would not be sampling from the correct distribution. Okay, and you can try for yourself in your project. If you remove this term and then try to generate data, nothing will work. Or it will work very poorly. We can also do this trick of interpolating between samples in latent space. Or maybe let's pick these two. So I will try to interpolate from this A to a 0, and I will do it in latent space using this piece of code. But so basically what you see there, so what is, so I encode both images into the Z space, and I use the mean, the mu output. And then I will linearly interpolate between these two mu, between mu of the first image and mu of the second, with a step which is proportional to the number of interpolation points. So in this case, it's 20. So we start, yeah, actually. So we start from this 8, which we encode. We get this one. It should be an 8. It should be the same, but it's not because the encoder is poor. And then we go smoothly in latent space from this one to the encoded version of this 0, which is at the other end. And then I just linearly interpolate between the two, and at every step I decode, and I do this there. Okay, and there, yeah, maybe it's not the most convincing demo in this case, but you see that, or maybe I can pick others for which it will work better. Yeah. You get a smooth transformation from one to the other. If we compare that to a linear interpolation directly in pixel space, you see that we would have one, on the one hand, only one image, this one or this one, and then in between, a slow disappearance of the first and a slow appearance of the second. Okay? Questions on this? Okay. Okay, so in the slides we have a similar example, a step-by-step example, where I start from the same MNIST dataset, and then I instantiate really the same VAE as I did in the code, almost, except for the decoder, which in this case is Gaussian instead of being this Bernoulli distribution. And so for the decoder, if we enumerate all the components, we start from a Gaussian prior, then we have a Gaussian distribution for the data, and we define an MLP between Z to the parameters of the data. And we have the mirror for the encoder, where we say that QZ given X follows the Gaussian, together with the reparametrization in terms of epsilon to produce the Z's. Okay, and in between X and parameters, we have an MLP. Okay, and these are choices that we make. Of course, you are free to pick something else. Okay, a VAE is not always and almost never an MLP for the encoder and the decoder. This is just for the sake of the presentation. Of course, you should use and put all the capacity and all the more advanced architectures that we have seen inside these two components. Okay, we plug everything, we arrive to the elbow, and then here you see other examples for a 2D, 5D, 10D, and 20-dimensional latent space, where you have more blurriness for low-dimensional latent space, and I would say crispier images for a higher dimensional space. But still, in my opinion, these images, they are not that good. If you compare them, these ones to these ones, you should be able to recognize if some image comes from the Grand Truth dataset or if it has been generated by this specific VAE. In the original, so these are results that have been presented in the original 2013 paper about VAE. And at the time, it was really good, and they also showed that you could do that on other images that MNIST, in this case, small images of faces. And again, you could also do this interpolation exploration of the latent space to observe or try to understand the structure which is learned inside this space. Okay, so this is something I've already mentioned a few times, but really this term, you may think it's not important, but if you remove it, nothing works. We could be tempted to remove it, but if we remove it, then we cannot generate data anymore. And also another effect of this term is that it's forcing also the structure of the latent space. It's forcing so it's in a sense regularizing how the latent space will be organized, how the information will be placed in this space. And so if we didn't have any KL regularization, then basically we would go back to an autoencoder and it would be free to use this domain as it wishes, okay? Which can be very good because it would improve the reconstruction, okay? But at the same time, it makes sampling from this space more difficult. If we regularize, then in a sense we are forcing the encoder, or we are forcing the latent space to be simpler. This is basically what will allow us then to sample from also sample distribution. Okay? So this KL term really is what enforces simplicity in the latent space and which will also indirectly encourage some kind of learning of the semantical structure of the data and also how it should be disentangled into the components of these latent vectors. Okay, some applications to finish for today's lecture. So they are not the most impressive applications because honestly these days VAEs, they are not used directly by themselves anymore. We use more modern generative models like diffusion models, but still I think there are a few nice applications. This is an application from 2016 where they show that you could use a VAE to compress data, and you could do that to compress images much better than regular image formats like JPEG and others. And so what does that mean? It means that you can preserve at some fixed compression rate, you would have a quality of image which is higher than with these classical JPEG formats, which is quite nice. Or indirectly, that means that for a target quality, the compression would be higher, so the resulting images would be smaller in size, okay, even though you have the same quality than if you were to use JPEG. So this is quite hidden, certainly to many of you, but you should know, for example, that every time you talk to someone on Teams, Zoom, or some other video system, the image is no longer transmitted in, it has never been transmitted in its raw format, okay? But now the compression scheme which is used by this system is based on neural networks of the kinds of VAEs. And why does that make sense? Because of course, this only works if you know in advance the kind of data distribution that you want to compress. Of course, JPEG will work equally well on any kind of image. But when you use a VAE, you are making also an assumption about the data that you will compress. And that's where you can gain, you have an advantage. It's because you know you will compress natural images, or because you know you will compress images of people in front of their laptop behind some background, that you know that there is some regularity in the data that you can exploit to obtain a smaller representation. But still, I think it's a nice example. Another example of what you can do with a VAE is this one, related to speech. And so this is a video to do what we call, not a video, an architecture that you can use to do voice style transfer, which is based on two components, an encoder that would take as input some speech in waveform, then would process this data, would produce parameters of a latent distribution, and then you would sample some vector z. In this case, the space is not continuous; it's discrete, but it's a detail. And then you decode these latent vectors back to speech. And what is nice about that, and that's something I've not mentioned yet, but when you look at the decoder, which will take this one, which will take some z as input and then produce data or parameters for the data as output, there is also nothing which prevents you from adding some external context as auxiliary inputs. Okay, so if you want to generate data conditionally on Z as before, but also conditionally on some context, you can do so by just adding one more input to the decoder. And this is what they do there to do voice styles transfer. So, for example, they would be recording someone's voice, then encoding this speech with its voice into latent space, and then instead of just decoding and reproducing the same voice, you can say, okay, I will add an additional input, for example, a speaker identity, and decode this speech in the voice of this speaker, which may be different from this one. Okay, and if you have a database of different speakers from which you can then learn this relationship, then you can start encoding your voice and then decoding it into someone else's voice, for example. And if you are curious, you can follow this link and you can listen to some samples that they've produced. Okay, a third application, which I find more interesting, is this one from chemistry, or computational chemistry, which is about how can you design new molecules that would have some properties that you want to, for example, maximize. So let's say you have a database of molecules, and you know properties about each of them, and your goal then is to find a new molecule, like a new drug, for example, which will maximize this target property. This is a difficult problem because molecules, they are defined in a non-continuous space. You have a discrete description of atoms and bonds and so on. But the quantity that we like to maximize very often is something continuous. So how could you do gradient ascent on the molecules to maximize this target property? That's something you can't do directly in the original space of molecules. However, if you have an autoencoder or VAE of molecules, then you can use this as a way to go from a discrete space of molecule to a continuous space of latent vectors. And then you can build a database that on the one hand you have latent vectors as input, on the one hand you have the target property as output. You can learn also the mapping between the two or approximate the mapping between the two with a third neural network. And once you have that, you can optimize now the target property. So, for example, you can do gradient ascent on the property, but now directly on the latents, which are continuous. So for which it makes sense to do that. And once you've optimized the proxy for the objective, that gives you a new Z somewhere in the latent space, which you can decode back to a molecule in the discrete space. Okay, questions on this? Okay, so that's it for today. So next time we'll see how to fix this, one of the problems I've mentioned, and then we'll arrive to the diffusion model. Okay, thank you.